going to the seminar.
Oh, I know, but were you able to get the password and everything?
Mute.
You can mute.
Yeah, no.
And also, I want to thank all of you for being here today for the seminar. Today I'm going to be talking about the seismic cycle mechanics of an active low-angle normal fault, the Mayu Fault in Papua New Guinea. And the first half will be some results from my PhD work at UT, and then we'll transition into some of the recent dynamic rupture models that I've been working on here at Scripps. And I also want to thank my advisors, Elise Gabriel here at Scripps, and also Lara Wallace and Luc Labier at UT, along with all the collaborators listed up here. So today we're going to talk a lot about low-angle normal faults, and one of the reasons why these are such mechanically interesting faults is that according to classical Andersonian theory of faulting, we expect that in extensional regions, our maximum principal stress, sigma 1, should be oriented vertically, and for crustal materials with Byerlee friction of 0.6 to 0.85, the faults that we expect, normal faults that we expect, should dip about 60 degrees. And reactivation theory, like as shown here in the Simpson 1990 paper, predicts that if we rotate our faults far enough away from their optimal orientation, so if we start at a reactivation angle of about 30 degrees relative to sigma 1, and we rotate the faults back until they're so poorly oriented that they should eventually lock up and become unable to continue to slip, we should then expect to see new faults forming instead of continued activity on the pre-existing faults. So mechanical paradox, because we see low-angle normal faults around the world. We see plenty of examples in the geologic record, but they've always been mechanically anomalous because it's difficult to explain their mechanical origins based on these classical theories of faulting. And so in addition to the low-angle normal faults we see in the geologic record, we also see some active examples. So down here at the bottom left is an example from the Alto Tiberina fault in the northern Apennines of Italy. And all these black dots are microseismicity that outline the shallowly dipping normal fault below about 4 kilometers depth. And then this green one is the Gubbio fault, which is a splay in the hanging wall that hosts some larger earthquakes. And then over here on the right is just an interpretation from Colatini's review paper of sort of the mechanical processes at work here with viscous deformation below the brittle ductile transition, and then frictional creep on the detachment with larger earthquakes on the splay faults. You can see, I like this figure because it shows the misorientation between sigma 1, which comes in at a really high angle to our fault plane. So these faults are thought to be misoriented. But nonetheless, they are really important mechanisms for rifting continental crust. They are really efficient at thinning the upper crust if extension localizes onto one main detachment fault, like is shown up here. Then they're able to exhume metamorphic core complexes, which are these intact structures in the footwalls of detachment faults that bring mid to lower crustal rocks up towards the surface. And these are commonly associated with most of your strain localizing onto one main detachment. And so some of the mechanisms that can help explain how we have these faults active at such shallow dips are the rolling hinge mechanism, which is shown a bit in this figure from Whitney et al., but shown quite well in these models from Labier et al. 2000. And the idea there is that your normal faults form at steeper dips, but then due to continued extension, the fault might be able to become quite a bit weaker than Byerlee values of friction. And that weakening allows the footwall to rotate back along a weaker fault in the near surface, which dips shallowly. And that leads to this formation of these domal core complexes like we see in the field. Another proposed mechanism that would allow low-angle normal fault activity is basically the rotation of your principal stress axes. So if the principal stresses are not Andersonian and instead sigma 1 dips closer to parallel to the low-angle normal fault, then the fault might not actually be misoriented, and it may actually be well-oriented for slip in the stress field. And this has been proposed for detachments like the Whipple detachment in the southwestern US. I just want to point out that these rotated principal stresses might not be necessary if we allow the possibility that these faults are actually quite weak, which is, it falls out of the geodynamic models that establish a rolling hinge. But basically the idea is that the mechanical paradox that I was just talking about all hinges on these rocks retaining Byerlee friction, even as the faults are more and more active. But I like the way that Avers points out that So here the limit of the lockup limit is this hydrofrac limit, and that's essentially where sigma 3 equals the pore fluid pressure, and we expect to start having new hydraulic fractures rather than continued slip on our normal fault. And he points out that for friction values of 0.6 or 0.8, we do in fact have a lockup limit with a normal fault dip of 30 degrees or so. But if you allow for the possibility that the friction of the fault is more like 0.4 or 0.2, then we're able to slip at much shallower angles. And faults dipping, 10 to 15 degrees aren't so anomalous after all. Colatini in his review paper then looks at some specific lithologies that have been found in exhumed longo-normal fault cores. So taking the frictional strains that's found in the lab from these exhumed fault materials and then plotting them. Sorry that this is sort of an inverse plot of what's on the left, but here lockup occurs when this curve of R goes to infinity. So for pretty standard crustal materials like granite, that's still somewhere in the 30 to 40 degree range. But for these weak clays like illite, smectite, and talc, we start pushing that possible dip of your normal fault closer to 10 degrees or so. So one of the longstanding questions has been whether these longo-normal faults can actually host large earthquakes or if they just creep aseismically. And one reason we don't have a better handle on this is that the active examples of longo-normal faults are pretty rare, and they typically slip at long-term slip rates less than a centimeter per year, which makes them hard to identify. But we have recently identified quite a few active longo-normal faults. And we know that they are microseismically active, which implies that they are creeping, as we saw in the Alta example. And also there's some GPS results like this Reinsdorfer and Bennett study. These are GPS velocities on the Y, and they've inferred locking of only above 2 kilometers depth. So essentially a seismic creep down dip of 2 kilometers depth, which would predict that these probably do not host large earthquakes. However, more recent studies have suggested that in fact we can have magnitude 7 or larger earthquakes on these faults. In the bottom right, starting here, this is essentially a study that looked at the same data that we just saw, the GPS data from Reinsdorfer and Bennett, but allowed for heterogeneous locking patterns and also locking on the splay faults in the hanging wall. And they found that a heterogeneous locking pattern, so here the orange or red colors are strongly locked that might host larger earthquakes. That this can explain the geodetic data equally well. We also see examples from the paleoseismic record, like the Cañada de Vida in Baja California, where the deposits in these shallow basins record large earthquakes on the underlying detachment. And in 2010, we had a 7.2 El Mayor Cucapar earthquake in Mexico. And Fletcher et al. Have looked extensively mapped this earthquake and the surface ruptures. Done quite a bit of modeling that shows that this earthquake seems to have nucleated on an underlying shallowly dipping normal sense detachment fault that then cascaded into rupture on many of these other faults in this complex network. And finally, there was a recent paper that has inferred that some historical tsunamis recorded in Indonesia actually were sourced by large earthquakes on the shallowly dipping banded detachment out here in the Pampas Sea. So all of this is to say that recent evidence points to the fact that these faults might actually host large earthquakes. And some of the questions that leads to are, how hazardous are these faults? Can they rupture to the surface? How do the earthquakes interact with splay faults in the hanging wall? And ultimately, can they generate large tsunamis from these earthquakes? So today I'm going to talk quite a bit about the Mayu Fault, which is located in southeastern Papua New Guinea. And here's just a regional tectonic map to give some context. We're in an overall region of Pacific Australian convergence. So the Pacific plate is colliding with the Australian plate. But we've got some pretty interesting microplate tectonics. So we're going to be focusing in here on this red line, the reactivated Owen Stanley fault zone. So the Woodlark plate here is rotating counterclockwise in response to northward subduction at the New Britain Trench and the San Cristobal Trench. And that's driving seafloor spreading out here in the eastern Woodlark Rift. So this is progressed all the way to seafloor spreading, and that rift is propagating westward towards the Papuan Peninsula, which consists of continental crust. So we're in an area of incipient continental rifting as this extension is propagating inland. And we'll zoom in now on this black box here. So right at that transition from seafloor spreading, which is this gray blob over here, we have distributed normal faulting through the Goodenough Bay. And And that seems to be helping exhume the Goodenough Island and Ferguson Island core complexes. But what we're really going to focus on today is the Mayu Fault over here further to the west. So extension seems to collapse and localize onto this one main fault, the Mayu Fault, which in its footwall, we have Mount Suckling and Mount Damon, which together make up the Damon-Suckling core complex, shown down here in the bottom right. And so this is one of the youngest and most rapidly exhumed core complexes in the world. You can see that it's retained its beautiful domal shape despite being exhumed in a humid environment. And that it's being exhumed along this really shallowly dipping Mayu Fault, shown down here. And some recent structural and tectonic geomorphology work has shown that the Damon Dome is evolving via a rolling hinge. So the fault at depth does dip quite a bit more steeply, as shown here by this microseismicity that delineates a creeping portion of the fault down dip of about 15 kilometers depth. So that area seems to be creeping with just microseismic activity and shows that the fault steepens at depth. And also there's some results that show that the top of the dome has been back rotated about 40 to 50 degrees from where it started down here. So, I mean, the rocks began their journey somewhere down here. And also recent geodetic and geologic evidence, so GNSS velocities as well as beryllium 10 dating of the youngest exhumed fault scarp show that the Mayu Fault is active at tip slip rates of about 8 to 10 millimeters per year. So all that is to say that the Mayu Fault is demonstrably active. And so what we were interested in part of my PhD work is looking at the interseismic deformation on the Mayu Fault via surface velocities recorded by campaign GNSS. So what I was interested in is installing a dense network of campaign GPS sites on the hanging wall of the Mayu Fault, because forward models show that this is the area where we would expect to see a signal of elastic strain accumulation from interseismic blocking on the underlying Mayu Fault. And then we installed a few sites on the footwall as well to constrain footwall motion. And so each of these is one of our campaign sites, and they're color-coded by which years we've measured them. The dark blue ones coincide with previous GPS sites from Wallace et al. 2014, which is shown up here on the left. And that helped establish the regional kinematics. We update some of their results as well, but we were able to tie into this well-established regional network. And the fieldwork consists of lots of boat and footwork. We're traipsing around installing these GNSS receivers for most of these sites, although we also took a helicopter up to mountainous sites, which gave beautiful views like this one over here on the right. So I'm just going to walk through a few of the results from this survey. The main one is the updated velocity field. So these are all velocities. Oh, the scale's a bit cut off, but here's 10 millimeters per year. And we're going to zoom in on this really dense cluster that's hard to see at this scale. So the next slide will show these velocities in a bit more detail. As you can see in map view, the velocities are generally increasing coastward. So that's showing the extension across the Mayu Fault as we move away from the fault trace out towards the ocean. And here we're going to be looking on the y-axis at the strike perpendicular velocities along a profile A to A prime shown over here in this map. So now we're pretty much looking at just the strike perpendicular extension component of these velocities. And the Mayu Fault trace is shown by this dashed line here. And I think this is a better way to see this coastward increase in interannual velocities shown here. So next I'm going to talk about some of the modeling that we do to understand these velocities. And a common approach is to discretize the crust into rigid blocks that rotate relatively independent of one another, except that they can interact along their boundaries where we prescribe faults. So we assume that these are rigid rotating blocks that can only accumulate elastic strains along their boundaries. This helps us to establish a regional kinematic frame in which to look at the individual velocities. And what we do is that we jointly invert for both the poles of rotation of our crustal blocks as well as the coupling on the faults that are bounding those blocks. And to do that, we input GPS velocities, regional fault and earthquake slip vectors, and the geometries of our blocks and faults. And the results of these joint inversions are this potentially familiar figure of Cascadia locking. So looking at the slip deficit rate that's accumulating in Cascadia. So basically the difference between the slip rate predicted by long-term plate motions and the actual observed displacement across this fault on interannual timescales. And so these warm colors are where we have a high slip deficit rate, where we might expect that we would have larger earthquakes, or the potential for larger earthquakes in the future. And as I mentioned, we had a pretty well-established frame of reference for these crustal motions based on Wallace et al. 2014, although we update this model as well with our new velocities. So I'll first just show the initial results that fell out of these larger joint inversions for the locking on the Mayu Fault. Interestingly, the preferred model only includes locking down to about 2 kilometers depth with deeper creep down dip of that, which would agree quite well with the previous results from the Alto Tiberina Fault. And sorry, just to explain this figure a bit better, the light pink is the more strongly coupled or locked regions that are falling out of the model, and the purple are the less coupled creeping segments. And so you can see on the Mayu Fault, which is the one we're interested in, we really have just shallow interseismic locking or geodetic coupling, really shown in this light pink right near the surface. We can then take, again, a profile y to y prime through these velocities and see that block rotation component predicts we would have about 8 millimeters per year of extension across the fault. But then this small contribution from the elastic component of locking brings down our predicted velocity curve to look more like this green curve here that fits the data quite well. But this also is not fully insensitive to our new velocities, the dense network, but it's the input constraints for this large scale joint inversion for regional motions. They don't let you zoom in and focus on a certain fault of interest quite as well as some more simple models do. So we took the results from this inversion and started doing just 2D dislocation models. So these are just simple Okada dislocations looking at the predicted surface velocities for different fault geometries. So different dips going from the shallowly dipping orange to the more steeply dipping purple fault, and different locking depths. And these are just examples of the effect on surface velocities that are predicted from these different more simple models. And these start to give us some sensitivity plots like this one. So we start to understand the trade-offs between locking depth and slip rate in terms of how they match our observed velocities. And we can see that for these models where we assume that the fault is locked at the surface and locked down to some depth before a creeping portion, we see that we need a slip rate somewhere around 10 millimeters per year and a really shallow locking depth. But one of the key assumptions here and in the previous Alto Tiberina study was that the fault is locked to the surface. But we know that low angle normal faults often have these really weak velocity strengthening clay-rich gouges in their shallowest portions, which might be able to host interseismic, aseismic creep rather than being fully frictionally locked. So what the models with locking of the surface come up with is, like I mentioned, this really shallow locking with deeper creep that fits the horizontal velocities decently well. But then we also started playing around with, what if we don't assume the fault is locked to the surface? What if we allow for some shallow creep on some portion up dip of our locked patch? And that's shown by these dashed blue lines in the fault schematic. And what falls out of this one is a model that fits pretty equally well, so pretty similarly well to the one with just shallow locking, but on a 35-degree dipping fault with a dip slip rate of 10.5 millimeters a year and locking from 5 to 16 kilometers down. So we ended up with these two very different geodetic locking models that fit the data pretty similarly well. So how do we move forward from here and test these different models? Well, we can go to the field and look for other geologic and geophysical evidence of recent Mayu Fault slip behavior, and then we'll come back and revisit these models a bit later. So one proxy for slip on the faults of interest here are emerged coral reefs in southern Goodenough Bay. So here now we're on this Goodenough segment over here in the east, and each of these stars on the map is the location of emerged fossilized coral reef platforms. So you can see that these corals are really well preserved. This is a pretty intact coral head over here. And if you look at these from a dinghy, what you see are these really pronounced series of platforms and then notches and then platforms. You can even see another notch forming down here at sea level today. I'll just point out that we think that this coastline is tectonically active or we thought that before we even went out there. Just based on, if you look along the shoreline, you see these beautiful triangular facets that are pretty indicative of recent fault slip and newly exhumed fault-related topography. So before we even sampled any of these platforms, we had the idea that it might be related to tectonics, but more of that on the next few slides. So how do these emerged coral reefs record the coastal emergence and the timing of emergence? Well, first, as a thought experiment, let's imagine that the corals emerge really gradually through the intertidal zone. So just gradual uplift associated with a creeping fault or sea level change. Then all of the corals would spend quite a bit of time in the intertidal zone where we have intense bioerosion. And we would, that intense bioerosion would erase any of the distinguishing morphological features of these coral heads, all of the geometries that we see well preserved in the field. However, if we have episodic emergence events, then as is shown in this diagram from Cal Stubbs' paper on in the Solomons, is that if you have really sudden emergence of up to a meter at a time, some of these corals can emerge above the intertidal zone without ever spending much time there. And so they're not subject to the same intense bioerosion that they would be if they emerged really gradually. So when we see these really well-preserved emerged fossilized corals, we can start to think it might reflect episodic and rapid emergence rather than gradual emergence. Just to get a handle on sort of the absolute magnitude of this emergence that we think would produce these coral platforms, we put a tide gauge out at our base station while we were sampling. And these are our results from the tides, which show that we have a mean tidal range of about 60 centimeters. So we think we need at least about 60 centimeters of rapid emergence to bring these corals above the intertidal zone and preserve them. So how do we actually sample and date these? Well, we go out in the field and we survey. This is my advisor, Luke, doing some surveying. We measure the heights and the relative elevations of these platforms relative to one another and relative to living coral level down here in the water. We then sample the most pristine, intact, in-growth position corals that we can find. So we want to avoid any that have terrestrial sedimentation that's infiltrated and turn them a brown color rather than this pristine white. So we measure their elevations. We send samples for ICPMS, uranium thorium series work to River Shen, who does the ICPMS work. And we end up with uranium thorium ages, which represent minimum ages of emergence of these corals, which is what I'll show on the next slide. So here we're looking at the height of the coral sample versus the age on the x-axis that's coming out of those uranium thorium concentrations. And these represent the emergence rates for the coastline. So each of these dashed lines, we have 1 millimeter a year, 2 millimeters, and 3. And you can see that most of our samples indicate emergence rates of like 1.5 to 3.5 millimeters per year, which is in line with some previous results from Paul Mann and Fred Taylor. And then we'll just zoom in on site D and look at the ages and elevations that we found there. We see 7 clusters of ages, so the dates tend to cluster around each other. And if you then plot in the substrate morphology, so essentially the platforms from which we sampled them, we have 6 preserved platforms that have 7 clusters of coral ages. And the only cluster that doesn't, that isn't associated with its own platform is cluster 3 right here. I'm going to talk a bit about that a bit. Unfortunately, there's not great along strike preservation, so we can't follow any of these platforms between sites except for a little bit at B and C. But it does seem quite reasonable that the youngest event correlates along strike, and then potentially the second youngest event, but it's tough to say for sure. Okay, so I mentioned that the coral platforms and the ages indicate episodic emergence. Shown over here, the modern tidal range is forming a dissolution notch at sea level. Then we have the most recently exhumed platform, and then the previous paleotidal notch. But emergence only means relative sea level fall. So there are different mechanisms that we could have that could rapidly emerge these corals. But we know that regional Papua New Guinea sea level has fallen less than about 0.5 millimeter per year in the last 6,000 years. And also that global sea level rise was relatively minimal up until the Industrial Revolution and around 1700, 1800s. So we don't think that there's any reason to think we had these wild fluctuations of local sea level that would have caused the platforms to emerge in this sort of pattern. And so if we have episodic tectonic emergence events, then we infer that those represent earthquakes, although we can't really say much about the specific timing of whether it was an accelerated creep episode, but most likely we're talking about co-seismically emerged corals here. So with our emergence results, we can start to play around with inferring paleo-earthquake characteristics from these emergence values. And what I just want to point out here in the bottom right is that we don't know the exact fault geometry at depth, which is one of our main limitations in this study, is that it hasn't really been mapped with seismic reflection. So we don't know if this co-seismic slip is propagating to the surface along a shallowly dipping detachment, or if it catches one of these more steeply dipping splay faults in the hanging wall, which would affect the surface displacement patterns and the emergence of these corals. But we can still look at some length moment scalings and width length scalings for dip slip earthquakes and start to just think about what size of earthquake we're talking about here. What falls out is that we're looking at somewhere around a magnitude 7.3. We get a range of like 7.1 to 7.6. And that usually includes seismic slip down to 15 or 20 kilometers down. Okay, next we're going to transition to just talking a little bit about the exhumed fault zone geology, which gives us a few more clues about the style of slip here. I know there's a lot on this slide, but I just want to point out the sampling location. So our colleagues at Victoria sampled exhumed fault rocks from all of these locations. You can see them relative to our GPS sites as well. And the fault core that they found is really well preserved, and it preserves the entire sequence from the protolith rocks, which begin their journey as metabasalts in the footwall down here. And they become sort of progressively cannibalized and formed and deformed into this series of fault rocks. So they're first sheared into myelinites and ultramyelinites down here below the brittle ductile transition. They eventually start being eaten up and formed into foliated cataclasites, which I'll point out host pseudotachylites as well. Finally, as they enter the brittle frictional regime, they further reduce their grain size to ultracataclasite, and finally, they end up forming these saponite-rich gouges, so these clay-rich gouges in the shallowest portion of the fault. So pseudotachlite is a glassy melted rock that's found in some fault zones, and it's usually inferred to represent co-seismic slip because you really need an earthquake to generate the heat pulse that would be necessary to melt the rocks in the fault and form a glassy melt at these depths. And so Tim Little has argon dated these pseudotachylites to an age of 2.2 million years. And with a slip rate of a centimeter per year, as we know, is the case for the Mayu Fault. These formed at depths of 10 to 12 kilometers. So the next thing that we do with these exhumed fault rocks is take some samples of each of the different units and then run some velocity stepping rotary-shear experiments in the lab. So Carolyn Bolton spearheaded these and took different fault rocks from the different units that I just described and ran them through different velocity steps at different crustal pressure temperature conditions. And here's what the apparatus looks like. The gouges are popped into this rotary-shear. And the results that are shown over here are the effective friction. So here's the applied shear stress over effective normal stress, which gives us the effective friction. And each of these little blips is one of the velocity steps that I mentioned relative to the full displacement of the experiment. You can see that for the saponite gouges shown here, the frictional strength is really quite low, less than 0.3 or 0.2. And what we also test in the lab is not just the frictional strength, but also the frictional stability. And I won't go too much into rate and state friction, but the rate and state friction parameters A and B are a proxy for whether these rocks are likely to slip unstably, which could potentially mean that they are seismogenic or slip during an earthquake, versus that if their velocity weakening, if A minus B is negative, relative to if their velocity strengthening and A minus B is positive, then an increase in slip velocity increases the frictional response, and we're more likely to arrest rupture and promote stable creep. All of this to say that we end up with a profile with either temperature or confining stress for the frictional stability response to changes in slip velocity of the different fault rocks in the Mayu Fault. We end up with a pretty standard profile, actually. So we have velocity strengthening at low temperatures and confining stresses. And then we have velocity weakening behavior at higher temperatures, consistent with deeper depths. And finally, a transition back to velocity strengthening at even greater depths. Okay, so as I mentioned, this is all to give us a bit more evidence to help test our geodetic locking models. I'm just going to run through the observations again. We're inferring Holocene earthquakes with magnitude 7 or greater based on the uplifted corals. Paleoseismic slip at 10 to 12 kilometers depth based on the cataclasites. I didn't mention this, but we have evidence for mixed frictional viscous slip in the cataclasites due to mutually cross-cutting brittle and ductile microstructures. And then, as I mentioned, that planar microseismicity down dip of our fault implies that we have mostly creep below 15 kilometers depth. And finally, we have these lab-derived frictional stability transitions from strengthening to weakening to strengthening. And these are consistent with transitions at around 7 to 15 kilometers depth. So all of these results point towards model 2, saying that we have stronger locking at depth and potentially some aseismic, interseismic creep both up dip and down dip of this lock patch. We'll run through this slide quickly, but this is just a recap of some of the evidence that the Mayu Fault might host large earthquakes. Like we've talked about, the corals record paleo earthquakes. Syntectonics are good indicators that the frictional results line up, and we end up with results pointing towards geodetic coupling that's strongest from 5 to 15 kilometers depth. So it seems that these active longitudinal faults are actually capable of hosting large destructive earthquakes, but we know very little about these quakes and what they look like. Can they rupture to the surface? How does rupture interact with splays in the hanging wall? And can they generate large tsunami? So what motivated my work here at Scripps is whether dynamic rupture modeling can help answer some of these questions about low angle normal fault earthquakes. So I just want to briefly run through dynamic rupture modeling and what it is and how it's useful. These are time-dependent forward models that simultaneously solve for coupled frictional fault slip as well as seismic wave propagation in the surrounding medium. And the slip in these models evolves spontaneously based on the fault physics you prescribe, the material properties around the fault and on the fault, and the initial and boundary conditions. And this is distinct from kinematic rupture models where slip is prescribed in those models. So the slip's evolving spontaneously in these. And the more we're able to constrain model parameters in dynamic rupture models with field and lab observations, the more we're able to reduce the inherent uncertainties in these families of models and start to work down to a pretty well-constrained group of rupture scenarios that seem plausible for the faults we're looking at. And these can be really useful for understanding fundamental coseismic processes like the interactions between different faults, as well as estimating sort of the realistic worst-case rupture scenarios for faults. These can be especially useful in margins that are currently seismically quiet, but that we know can host really large earthquakes, especially, for example, like Cascadia, where we know there will be a really large earthquake, but there hasn't been much since the installation of the instrumental record. So they can be really useful for coming up with realistic families of rupture models. So now I'm going to switch and talk a bit about the work I've been doing here at IGPP, which has been to integrate a lot of these observations for the Mayu Fault into constraints for dynamic rupture models. So here, we're taking our fault geometry from Weber et al. 2020, who came up with a surface model that matched the mapped fault tips at the surface from field mapping, along with the microseismicity at depth. And what's being shown here in the colors on this fault is the effective shear stress in the down dip direction. A bit more about that in a sec. We take our mechanical and material properties, so density and the elastic moduli, from Abers et al. 2016. They did some tomography and receiver function work, and we take their profile right beneath the Papua Peninsula. Finally, we apply this deviatoric stress decay below about 12 kilometers depth, and that's consistent with paleostresses. So there's a peak differential stresses recorded in the footwall of the Mayu Fault that peak around 6 to 12 kilometers depth. And then we apply a decay in shear stress below 12 kilometers down to 15 kilometers. And that shows up in this figure at this sort of relatively sharp cutoff where shear stress drops below 15 kilometers depth. And finally, I just want to show that our meshes are fully 3D and that we refine them close to the fault. So we're always doing full 3D simulations. We're refining the mesh close to the fault to resolve the on-fault slip processes. And so this example up here is looking along the strike. You can see how the mesh is refined close to the actual fault surface. Okay. We've already talked about this, but the friction on the Mayu Fault is pretty well constrained from the field and lab experiments. And so in our dynamic rupture models, we are extrapolating the results from the lab onto a fault profile with depth based on, so these are syntectonic veins, and chlorite within the syntectonic veins gives a deformation temperature. And so we can map then different fault rock units with temperature and then with depth, and then apply the friction properties, the rate state friction properties from the lab, mapping all of those with depth into a nice little A-B profile, like this one over here on the right. Then we apply pretty standard other friction parameters that we don't have as good of a handle on. And so we use a rate state friction formulation that is pretty standard, but has enhanced velocity weakening at truly coseismic slip rates. So this comes out of the work of Julia DeToro's group that shows really enhanced weakening once we hit seismic slip rates. And we use the formulation from Goodenough et al. 2011. So fast weakening above the cutoff velocity AW. And finally, here's just another example of what our fault model looks like. So again, I'm showing the total shear stress, and then this little patch here is how we impose our nucleation procedure. So for 1 second at the beginning of the model, we apply an overstress to apply an extra 30 MPa traction down dip that nucleates the earthquakes that we'll see in the subsequent slides. Okay, so with this first set of dynamic rupture models, what we wanted to test was whether detachments are well-oriented or poorly oriented for slip, and what the coseismic effects of these different stress orientations are. So this is really important because that El Mayor Kukupar earthquake, which I mentioned, is sort of our best example of a low angle normal fault earthquake. And it's been proposed that the detachment served as a keystone fault. So essentially, the detachment is poorly oriented relative to the regional stress field, but all of the faults around it are relatively well oriented. So these steeper faults are well oriented. They are then critically stressed to failure well before the detachment is, but they can't rupture until the detachment itself is critically stressed to failure. And that's represented over here on the Moore Coulomb diagram. These green stars won't reach the failure envelope until well after the red dots from the well-oriented faults do. And so the idea is that these better oriented faults in these detachment systems will lead off all of their excess shear stress via microseismicity and small earthquakes, but they can't rupture in a big earthquake until whatever detachment controlling their slip is stressed to failure. So testing whether these detachments really are poorly oriented is interesting to look at the coseismic effects of that. So in the Mai'iu Fault, there's been some paleopiezometry work done both in the hanging wall and footwall. And basically what falls out of that is that our stresses in the hanging wall appear to be Andersonian with sigma 1 oriented vertical, whereas the stresses in the footwall appear to be inclined such that sigma 1 actually points back towards the fault surface, and the fault is actually more poorly oriented in this stress field than it would be in an Andersonian stress field. And finally, the other scenario that we test in terms of the applied stresses is what I mentioned early on. So one of the models for how low angle normal faults continue to slip is that the sigma 1, the principal stress, is actually rotated to be well aligned for slip. So if sigma 1 dips more parallel to the fault surface, then this fault could remain active at lower dips than expected. And so we wanted to test all of these different stress scenarios with dynamic rupture models and see what kinds of earthquakes result from those. So here, this first example is Andersonian extension and constant Byerlee friction. So we're using a static friction, effective static friction of 0.6 at all depths, and then applying just Andersonian extension. What I'm showing here is the resolved shear over normal stress, which is a good sort of a priori indicator of the slip tendency. So where we see warm colors, we expect the fault might be well primed for slip, whereas where we see cool colors, like below this rider block, where we know this portion of the fault is abandoned, we can see that in the field, and it also has a low resolved shear over normal stress. In the second case, we're now looking at the well-oriented stresses. So now we let sigma 1 be rotated to dip or climb to 60 degrees towards the north, essentially, which lines it up better for slip on a low angle normal fault than it is when it's vertical. And on the same color scale, we fully saturate. This fault appears to be, really well primed to slip. And finally, the other alternative is where sigma 1 dips back and the fault is more poorly oriented than in the Andersonian case. Here you can see that the general patterns still match the initial Andersonian case, but the magnitudes of the shear over normal stress are much smaller. We don't expect as much slip in that case. I'll just walk through some of the results. This is for the reference model, which had Andersonian extension and the constant static friction. You can see that after 1 second, our nucleation procedure has stopped being applied and slip starts to propagate out from the nucleation patch. It propagates along the strike, and it also propagates up dip, but reaches a depth of about 6 kilometers where it stops propagating further up dip. And finally, at the end of the model at 15 seconds, we do see some slip near the surface. So rupture reaches the surface on the Goodenough segment over here. We can see what that looks like in terms of surface displacements. So here we're looking at the vertical surface displacement resulting from the slip pattern shown on the left. Substance in blue and uplift in red. You can see that there are these wave-mediated patterns out here on the edges. Those are the displacements related to the waves that are passing by. And what they're leaving behind is the static displacement pattern shown in the dark blue smudge here. That becomes apparent in the 25-second snapshot, where we see we have about 1.2 meters of hanging wall subsidence in this model, which lines up quite well with where we see about 1.2 meters of coastal emergence recorded in the corals along the coast of Goodenough Bay. We've already looked at this figure, but we're seeing similar paleoseismically recorded emergence magnitudes as we are to those in this model with just Andersonian extension applied to the fault. As I mentioned, now we'll just look at a few of the other loading scenarios that we've tested. Just to get our bearings in what these plots are showing, we're still looking at slip in the colors, but down here, each of these contours shows where the rupture front has reached after 1 second, 2 seconds, 3 seconds, and so on. And the color scale down in the bottom plots is a bit different as well, because this one saturates in the second example, which has stresses well oriented for low angle normal slip. We end up with a relatively large earthquake, 7.8, with up to 12 meters of slip, rupture propagating all the way into our velocity strengthening borders. And you can see down here in the rupture contours, this strange avocado shape in the rupture contours is indicative of super shear rupture. So we're seeing essentially unrealistic rupture velocities up dip of our nucleation patch in the model with well-oriented stresses rather than standard extensional stresses. Finally, in the case where we constrain the applied stresses based on the footwall paleopiezometry, we see that it's really hard to nucleate an earthquake. And in this example, I've actually increased the nucleation traction, and we're still not really able to trigger any unstable seismic slip outside of the nucleation region. So slip is pretty much constrained to wherever we apply that nucleation. So we don't think that fault stress under these conditions are likely to host a large earthquake. Finally, I'll just show a few more scenarios. Oh, this is cut off a bit, but again, this is our reference model where the effective friction is constant with depth at 0.6. But now we consider the possibility that the stress on the fault is modulated by the decreased friction in the shallowest portions of the fault, which we've seen in the lab. So we first try a profile with decreased friction in the upper 12 kilometers, that's the red dashed line. And then we'll try one with decreased friction only in the portion where we see velocity strengthening materials. So the red dashed line for the 12-kilometer decrease, that clamps down on the shallow slip quite a bit. You can see that now we just have buried rupture that doesn't reach the surface along any of the fault. We end up with a magnitude 6.9 that is pretty limited with depth. Then in the case where we only have a decrease in friction where we have velocity strengthening materials, but we also decrease the dynamic friction F naught according to that same profile, we end up with shallower slip, so slip that starts to reach towards the surface but doesn't actually quite get there. And once we have no surface rupture in this case, although we still have magnitude 7.1. I just want to point out that one interesting result that might result from these models with buried rupture is that we have increased post-seismic shear stress up dip of the rupture patch. So this sort of golden halo of total shear stress shows where we have increased shear stress after the earthquake. So if we have buried rupture on the deeper part of the fault, then we're applying some increased shear stresses on the shallower portion of the fault, which potentially could help drive either shallow afterslip or shallow intraseismic creep, which is in line with what we see, at least in our preferred geodetic locking model, where we think that we might have some shallow aseismic creep during the intraseismic period. Finally, this is some really new work in progress. It's not fully there yet, but we're starting to work on splay faults. And so we're incorporating splay faults in the hanging wall of the detachment, like I mentioned. We see it in detachment systems globally. So we're testing the effects of different splay fault dip angles. So again, here's our reference model with no splays. We have rupture to the surface on this portion of the fault. But as soon as we introduce one of these splay faults and we intersect it with the detachment, especially in the case of the synthetic splays, they take over a lot of the near surface slip. So you can see that we're no longer slipping to the surface on the detachment. I know the angles here are weird, but a lot of that slip ends up on the synthetic splay fault here and here. And it sort of limits the actual surface displacement related to the detachment itself. It's more prominent in the synthetic splays, which are the top row, although we still do see some slip occurring in the antithetic splay cases as well, although it doesn't limit surface rupture quite as prominently. And finally, where we're headed with this is that we would like to understand how these different splay faults affect the surface displacement patterns, because that's what would have an effect on tsunamogenesis if the seafloor displacement patterns are significantly different with and without splay faults in the hanging wall. So here on the left is again the reference model. We're seeing this sort of distributed subsidence pattern in the hanging wall, this blue blur. And then in the cases where we have splay faults, we're seeing enhanced and more localized seafloor displacement. Well, some of this is onshore, but we're seeing localized hanging wall subsidence rather than the more distributed patterns that we see without splays involved. And so, especially in the synthetic cases, that pops up by these really dark blue patterns that are bounded by the splay faults that are slipping. And it also even pops out a bit in the antithetic models as well. And I mentioned this is preliminary work, so this model didn't quite say it properly, but we'll have results from that one soon. And so this is where we're headed, is to learn some more about the display fault activity on these detachments, how they interact with slip on the detachment itself. I know there's been a lot. I'm just going to leave most of my conclusions up here, but I want to point out that we're finding that the modeled earthquakes are matching paleoseismic record with standard Andersonian extension, and we don't need to rely on any sort of abnormally rotated principal stress orientation to explain coseismic slip on low-angle normal faults. Some of the future directions we want to go in is to start constraining these dynamic rupture model stresses, either geodynamic models or seismic-cycle models. Also to look at the resulting tsunamis from these different models. And finally, to start taking these sorts of methods to a seismic quiet subduction zone like Cascadia, to learn more about the different geodynamic effects along the strike of Cascadia. So thank you for your attention, and I'm happy to take any questions.
Question for the personal.
I have one question about the rotation of the principal stress. So you have the measurements from the geological data. Can you explain why there is a rotation for the principal stress?
Rotation of the stresses or rotation of the
For the principal stress.
the paleostresses?
Yeah, the paleo stress or the second one that is not Andersonian.
Yeah, totally. So that falls out. Sorry, all the animations. It's really hard to get back there. So you're talking about this. So this was done with calcite twin paleopiezometry. So taking, I'm not a structural geologist, but essentially they're able to invert for the principal stress directions when these calcite or when these syntectonic veins formed and when the calcite twins within those veins formed. And so they are sampling these rocks once they're all the way up here in the exhumed footwall, and then running these paleopiezometry analyses to invert for the principal stress directions while they were deforming. And then they rotate those results back into the frame of reference of where were these rocks relative to the fault when they were deforming. So you sort of rotate your results back down to where you think that deformation happened. And then you look at your stress tensor at that depth. And what they find is that they always end up with this sigma 1 that's oriented even more poorly for slip than you would expect. So this was a really surprising result for the structural geologists to see that pop out, but it seems to be pretty robust. But one interesting thing there is that if these results from the paleopiezometry are right, then it seems like what the fault itself is feeling might be more limited by the hanging wall stresses, where we have weaker rocks in the hanging wall that might sort of limit the strength and stress that can be felt on the fault itself. That answers the question. Yeah.
Another question. Sure. Why do you think there are splay faults?
That's a really good question, because the idea is that our detachment would be quite a bit weaker than the intact rock in the hanging wall. And so, I mean, my thought is that the splays initially formed coseismically as a bit of a dynamic effect. So we haven't looked too closely into what the trapped waves look like in the wedge, but we assume there are quite a few waves bouncing between the fault and the through surface. And if those sort of locally exceed the strength of our sediments in the hanging wall. So yeah, Vivian mentioned that the hanging wall is full of relatively weak sediments and our footwall are these really strong metabasalts. So if you have all of these waves trapped in there, you might just locally exceed the strength of the hanging wall sediments and pop a splay fault that then is weaker in subsequent seismic cycles and continues to be active after that.
So there are no field observations from impact. You have geological surveys. Do you see any evidence of existing splay faults?
So there's evidence of splay faults in the hanging wall of the Mayu Fault. I don't think there have been any observations of splays forming coseismically because we really only have one earthquake example in the modern record, and a lot of those faults weren't well mapped to begin with. So like the detachment wasn't mapped beforehand. So So I'm not sure if they've seen any like news plays forming co-seismically that they can pin to one earthquake, but well, I don't have a great figure to show it. There's some seismic reflection offshore of the Goodenough segment of Mayu Fault that basically out here, there's some seismic reflection that shows that the hanging wall is pretty heavily faulted there. So we think it is pretty reasonable that we might have co-seismic activity on the hanging wall fault as well. Question, thanks.
Yes, nice talk. The two locking models that you have considered, they're very difficult to distinguish based on the horizontal velocities, but vertical velocities seem to be quite different in the near field. Of course, this is where GPS has the lower accuracy, but I'm wondering if you considered using interferometry, for example, and are the surface conditions even feasible for interferometry there?
Yeah, great question. So first on the topic of the verticals, we've looked at those and they can potentially distinguish between the two models, but we just didn't really trust them because the uncertainty bounds are so large that it didn't really seem like we could confidently say that they were reflecting the tectonics here or the same signal that we were looking for. But potentially we could remeasure and bring down those uncertainty bounds if we ever went back and remeasured these. In terms of INSAR, I have tried a few different attempts to get INSAR to work here. And it's, I guess, tough to tell here, but basically everything here is covered in really dense rainforest, except for like the very top of Mount Damon. So there's this little halo of ground where you can get some coherence in the INSAR. And then, oh, sorry, you probably can't see where my laser pointer is showing, but at the very top of the dome of the footwall, there's a patch that is coherent. And then out here on the coast on Cape Bogle, there's a gap in the trees and you can get some coherence there. But we were never able to I guess, unwrap all the way across this big, so there's this big gap in coherence where we have the rainforest. We were never quite able to unwrap between those two and get a deformation signal between the top of the footwall and the coastal hanging wall. But it would be really cool if there is a way to get a coherent signal across there from the INSAR. That would really help.
Okay. And just a general question, it's been a while since I looked at this, but if you look at the global catalog of focal mechanisms, are there any historic low angle normal fault events?
No, so yeah, that's one of the big things motivating this is that there are no well-resolved focal mechanisms of like more than magnitude 6.2 that have a low angle normal sense focal mechanism. And one of the suggestions more recently for why that happens is that anytime you would have a low angle normal fault earthquake, you might also be activating all of the normal faults around it, especially if following that keystone fault hypothesis. Then by the time you're rupturing the low angle fault, all the other normal faults will also rupture with it. And then I guess the focal mechanism that you resolve from your data would then include the contribution of quite a few different faults that would skew it away from looking like a low angle normal fault earthquake. But that's just been proposed recently. I don't know if that is really the explanation for the lack of these earthquakes in the record.
Yeah, well, just to comment on El Mayor Kukapa, the seismic moment release was very clearly dominated by strike slip motion. It's true that it may have nucleated on some low angle detachment, but the earthquake itself was 90% strike slip.
Yeah, I mean, that's interesting to think then, is that truly being controlled by the detachment or was the detachment just sitting there and feeling the effects of co-seismic rupture in a strike slip event?
Thank you.
Sure. Yes. Yeah.
I have a question about the block rotating models. Can you go back to that slide?
Yeah.
Oh, that one. I'm not very familiar with this kinds of plot. What does the width of each band in? Is that?
Oh, sorry. So these colored areas are the fault, and so
Oh, okay, so they are fault surface projected to the surface.
Yeah, sorry, I didn't describe this figure well. The dashed black lines are the fault traces, and then down dip of them, we're showing the Mai'iu projection of the fault. And so that's why this Mai'iu fault is so wide, because it's dipping so shallowly.
Oh,
that
I see.
It shows up as this wide band, whereas steeper normal faults, like the ones bounding the Dr. Castos, are just going to be these smaller bands, like this one here.
I see.
The colors are the geodetic coupling that's resolved from this block model.
Okay, thank you.
Thanks.
So if there is no more questions, thanks again for the wonderful talk. Yeah, so this will be the last talk this quarter, and we will restart again in January.
Thank you, Jianhua, for organizing all these talks.
Yeah.
And also Dan.